Time for another draft science video presentation. Yeah. Not produced well enough to be a production, but anyway. So we'll do a Google thing first. Really just go back to the original story, and that's just so glaring. So Google when Google arrived, here it was this highly polished, very fast, so they had good servers. Some money had to be spent on it, clearly, okay, and no ads and for free. And yeah, some people ask the question, how can they give it away for free? What's the catch? There's got to be a catch, right? There's no free lunch. But nobody asked the question too hard, and nobody tried to answer it, and so it was just kind of, Google got away with this for 3 years, just playing the game. Well, 2-something years, whatever it was, a number of months. Well, no, a number of years. And just watching the rest of the players in the market, Alta Vista being one of the main ones, Yahoo, and the dog one. What was that one? Legos, some kind of dog that went and fetched your shit. There was an Ask Jeeves, there was other different things, but they were all based on different mechanisms for indexing. Yahoo wasn't really a search engine, it was a directory. And all of them got kind of desperate because they had to make money to compete with Google. And so ones like Yahoo got pretty corrupt in the sense that they just basically, you just paid for a listing. They just forced you to pay money to basically be indexed. $50 a year. So, it got started to get ugly just because the competitors just didn't have any way to compete with something that was free, without, damaging their product, putting ads on it and other things to corrupt it. So, Google took the market. The tricky part was when Microsoft, who then was the king of the browsers, because Internet Explorer was used by 95% of the people back then, was going to put ads, allow people with web pages to buy an ad, and they would put the ad in the browser. So the browser would produce the ad. So instead of the ad being displayed in the web page, the ad would be displayed in the browser. So it's very much like AdSense, except the ads would be more efficiently served, and blah blah blah. Well, everybody went crazy. Microsoft was evil, blah blah blah. So at that moment, Google must have been panicking a little bit, because all of this venture capital must have been provided with the understanding that, yes, we're going to Shanghai. I mean, we're going to, well, whatever the word is for, we're going to blow the bomb up, and in this sneaky manner, and reveal that we really do have a plan, and the plan is to put ads on all the web pages on the internet. So they must have panicked a little when they saw the reaction to what happened with Microsoft. And at the same time, so you could sort of see that there was a related move that Google did, sort of another Microsoft kind of move, where there was a whole industry basically devoted to watching the search engines, just because of the possibility of corruption and cheating in the results. And this had already started to migrate into, they had already been corrupted by this whole thing called search engine optimization, SEO, where everybody was trying to fiddle with their keywords, put extra keywords in, put invisible keywords in, do all kinds of stuff to make their website show up. When somebody typed in porn, they'd want their website to show up. That kind of crap. So this was happening at the same time. So all the metadata was all being corrupted. There was the Whois database didn't mean a thing. I had been arguing that they shouldn't guarantee that the keywords have integrity, and it should be in the Whois database what you are pretending your website is about, so everybody can see it and see who's cheating, and they can be punished and fined and whatever. But anyway, so everybody's trying to cheat the game. And so that industry that was supposed to be watching the search engines became just, giving people information on how to manipulate the search engines. But anyway, they still had some watching. They actually had a website called Search Engine Watch. And it all got bought out by Google. Google went into all of these websites and found out who the key players were and hired them. That simple. So just hired them out of the game. So they all kind of just crumbled. So all the watching, all the blogs that were inspecting, all the popular, fact checkers were basically taken out of the game. And then Google went public and hit everybody with the big surprise that, oh, no, it's not really for free. We're going to put ads on every web page on the internet. So instead of just a few ads on a search page, you're going to have ads everywhere. But anyway, and they got away with it because there really wasn't anybody watching anymore. Nobody to make any noise. The noisemakers were shut up and gagged and, blah, 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 blah. So Google was clearly evil. Like I said, it's in their founding documents. The sentence is right there. There needs to be a non-commercial alternative. They never intended to be that. It was just a lie. So anyway, Baldy Catz, he's just a cowardice little shit-talking scumhole. The whole shill thing is such a fake. This whole, I don't even know why people like AB Science would even be connected to it. They make videos now where they just go out on the internet and find hidden camera crap and, just all kinds of little fail videos. So somebody videotapes you slipping on your front steps and, your big fat ass flips up in the air or something. They think that's informative. We need more people to watch people falling down and laughing because it's just so fucking funny, So anyway, I'm not saying once in a while you can't, laugh at a news broadcaster in Alabama, but I'm just mean it's just no point. It's not something we need a whole group of people to direct people to as this is what you should be doing with your spare time. You should try a little harder. So it's just despicable turds. They're just feeding the idiocracy and feeding it at a price. They're trying to collect their revenue. Whole thing is quite despicable. But it's the world we live in. Oh, it is recording. Alright, so on to the higher quality content. Richard Feynman, will continue with him. Lots of, there's always good stuff in these videos, just little bits and pieces where, you say, yep, that's a key point in the history of physics. That's one of your mistakes. So, this was the lecture in Auckland, where he's basically saying the same thing he said in the earlier 60s lecture, where he's basically saying, God does play dice with the universe. He's basically affirming Bohr's contention that it's a wooey-verse. It's not a mechanism. It's not cause and effect. It's at its elemental level. It's just making it up somehow.
See, as it settles, of course. Reflections are a happy thing in art pictures. There's moonlight reflected from the water. You have a window. When you look through a window, there must be a good example. Right back there's one. You look at a window, you can see through it, but also some reflection. Now already?
Right, so it's a kind of a simple thing. It's a thing that Newton had to deal with, and they still really don't have a coherent answer for exactly what happens when light reflects. They know some of the consequences, some of the effects, but they really don't understand causes at all. They can't draw you a picture of an atom and show you the light coming down, hitting the atom, and creating the reflection. They just can't diagram it because they really don't understand it.
There's a problem. Because the light that's reflected is not as intense as the light that's shining.
I probably need more volume, right? Right. Probably. Oh yeah, we run into this problem. Oh god, it is a little bit irritating that you can't just, you can't put that thing in the background. It's a little irritating. Oh, I have the volume all the way up. So, you're out of luck. I don't think I can fix it with any other setting. Maybe I will pause to try to fix the volume. Shit. Alright, really couldn't do much about it, so he just said some of the light goes through.
The window, say, or through the water down in. Only some of the light comes back. If the light is headed for water, for example, straight down, only about 2% reflects.
So he said 2, he should have said 4, so just pointing it out. Just minor error, but just for clarity. And it's really 8% because it's 4 off of each surface. Or it's 2 off of each surface, whatever. So the idea is, okay, I have to move that over, quite obviously. That should work out fine. Yes, that works out just fine. There's just no good way to do this, is there? Okay, so I can move him out for now. Alright, I'll do that. Alright, so light comes in, part of it refracts into and part of it reflects. Like 4%, or this percentage can be any percentage actually. So they're really just talking about the average or the perfect. Straight in, straight back, it would be 4%. The higher, the more the angle, the more the percentage that reflects. What else is key to understanding it? So there's something called the reflective index that sort of tells you that, but the fact is you can polish glass, you can change the shape of the surface, and that will change how much light reflects. Alright, so it all really depends on what you think light is, what you think's reflected. So the idea would be as if light, you thought of it as a whole bunch of stuff, a whole bunch of photons and pieces, that they're composite objects at a frequency. Then you could understand that maybe some of these little bits would reflect, okay, and some of the bits wouldn't. So the reflection would be made out of some bits that hit electrons and reflect back, and some bits that don't hit or reflect. They don't hit the electrons in that negative way. They hit them in some way that moves the whole atoms, and then the light goes through the atoms. So there's 2 ways to transmit. So it's sort of like movement. Movement a certain way doesn't create any sound and just makes heat. Okay, it just kind of creates a bunch of things that spin around and move around, but nothing moves really straight. But if I move quick enough, I can force a jiggle that is in primarily one direction. Okay, I can make the energy move in straighter lines. It won't. So when it hits, if it's a slow amount of movement, you can get a lot of deflections. You can get a lot of stuff that doesn't go really straight. But if I hit hard enough, then it goes straight. The energy goes straight. And that's really what's happening on a surface, is that there's a difference between the light that hits a certain way it hits. It goes straight through, kind of unencumbered. If it hits a certain other thing, okay, like a proton instead of an electron, it reflects. And it's really just the bits that are reflecting. It's not the whole photon. So you're not reflecting a whole photon, you're just remaking photons. So we're back to sort of the interference argument. There's not interference. There's just breaking photons and then remaking photons. See, they should do an experiment where they calculate the total energy. They take the total energy of a beam of light, and then they measure the total energy of all the reflections, and then the total energy of all that's transmitted, and see if there's any losses. And I'll guarantee there's going to be. I'll not guarantee it, but I am quite certain there will be. Quite certain. Alright, well, this is a little bit cumbersome, but we'll do it this way for now.
What does that mean, only 2% reflect? That means that if we had a photon counter here, let's say, draw the experiment so you know what I'm talking about. hard to make a water surface that's vertical. Yes, so we'll make the water surface horizontal. And light's coming down, and some of it's reflected, and we put a counter here to see one of those photo multiplier things, and we count the count. And we know how much we should have got, and we find 1. How can it be partly reflected? When, I forgot to say when I was talking about the party, when you have light of a definite color, the energy that the first one knocks out is always the same. Each particle is the same strength. There's no half particle.
So the photomultiplier, the first piece of it doesn't push out an electron. That's really what's deciding. Either push out an electron or you don't. So there's no half a photon, but that's again because that doesn't mean you didn't get energy, didn't mean you didn't get frequency, didn't mean you didn't get stuff, it just means you didn't get enough to kick the electron. And that's really all there is to that. I mean, it's sort of the photoelectric effect, and you're just saying with any kind of photonic radiation, like a photodetector will pick up infrared, where if you do the experiment at lower voltages, then you're doing the photoelectric effect, where you're saying that only ultraviolet light or blue light can kick an electron. So what was I going to say here? So the point is that if you try to draw this surface as atoms, then you can sort of understand this much better, that there's atoms here. And for the time being, just forget about the electrons swinging around. You just know there's nucleuses and there's electrons in positions. And the thing about glass is it's a crystal, which means all the atoms line up in a certain way, so they all have a similarity to them. So what you're really doing, is that you're sending light in straight down. You have a lower probability of hitting a proton, but if you send the light in at an angle, you can see more light can hit protons because they're not, they can get in between the fence of the electrons. So the electrons are a fence, and the protons are behind the fence. And if you want to get through a fence, sometimes going through this way won't get you what you want to get, but going through at an angle opens up your capacity to get deeper and deeper. The angles can be to your advantage in the geometry. You can navigate the geometry better at the higher angle. So it could be something simple like that, is deciding what's reflection and what's what goes through. The other point to make is there's a phase shift, on the reflection. When this material is denser than this material, and so let's just assume empty space here, and we'll just say any material here is going to be denser, so there'll be a phase shift, which means the electron has to do, or the proton, whatever's causing the reflected bits, is got to do some sort of movement before it makes the new photon. So it's slowing it down a little bit. And we know the light travels through the material slower than the speed of light, so we know it's probably doing a lot of not perfectly straight lines before it gets to the other surface. But the understanding is that these are atoms, and that these atoms are in crystals, and that the crystals have very specific reactions. And we know that glass must have a crystal that is long, going through for light to be transmitted through it. So whatever its geometry is, there's a consistent geometry in at least the direction of the polished surfaces. And so the bottom surface is in fact communicating with the top surface, in the sense that these atoms are arranged so that the electrons aren't parallel to each other. So obviously they'd be staggered. One atom would be there, and then the next atom would be here in the next row, and then this atom would be here, to maximize the distance between the electrons and the distance between the protons of the different atoms. There would be a geometry that the glass is in. And so obviously when you polish the surface, you're changing who's a peak and who's a valley on the surface. And as you do that, you're also changing the bottom. Obviously, the number of atoms, if you knock an atom off in the process of polishing, you're changing, the number of atoms, and in turn, you're going to change the position of the atoms at the bottom. You can't change how they're aligned at the top without changing how they're aligned at the bottom. So whatever you do to the top surface, you're technically also doing it to the bottom surface.
A full photon. What you get is full photon. But if the light is dimmer, what does that mean? There are fewer of them, right? Simple. So, of 100 that come down here, perhaps 4 out this way and 96 go through.
So that's just an assumption that of the 100, you didn't break any of them in the process. So he's basically saying you have 100, you get 96 through, you get 4 out. Maybe not. No, but plainly, maybe that isn't the truth. We don't have any hard evidence that that's the truth.
What determines which 4? Which one that's coming down of the 100 knows what to come back up? Right?
So again, if it's just the imagining of what a photon is. So they keep saying it as if there's only 2 choices. That it's some kind of wavy thing, whatever that would be, some sort of field disturbance, that affects, again, single electron, which doesn't make any sense because, the wave disturbance is gigantic compared to the size of the atoms even. 2,000, again, the polarization of light is 2,000 atoms, okay? I mean, it's huge. So there's no point in talking about this giant thing hitting 1 electron. And when they do this wave thing, they never talk about the fact that the wave has to have at least, a full node to node, peak to peak, for there to be a frequency. So we know that light is sort of a composite, in the sense that it's got more than one little thing in it. It's not just doing this. It's got to go all the way back up to this. You have to have a point to point to have a frequency. And so the thing I would say that, was always intuitive to me to think of it as, they're thinking that when they make it a particle, they're thinking it's a gigantic thing, and they're just tied to each other. Like this is a photon, and this is a photon, and the frequency is their size. When the exact inverse of that, which, oh shit, sorry. I have to find a better way than this, obviously. The better way to think about it is that the photon, the quanta, the energy of the photon, is a little bit separated by a distance, and then separated by a distance. So this goes back to getting really elemental. So if I was to argue that the whole universe is really just made up of this idea that there's energy in the universe, these little bits flying the speed of light, and that the electron and proton are really just nothing, a big 0. And then all you're doing is transferring the energy. So this bit sticks to this thing, and it drags it along for a while. And in the process of dragging it along, that is pushing it, it goes a little slower than the speed of light. So you could understand that if all I had in the universe was 1 electron, you could understand that at any one moment it would be getting hit by different pieces from the universe. And if all that happened when another piece hits, okay, this piece flies back off, this piece reflects back off, and then there's nothing stuck to it. And then the next piece comes in and sticks, and then the same process happens. Another piece hits, this one flies off, this one flies off. So you could sort of understand it's just conservational, and at any one moment this electron will be moving this way or that way or that way. And it just depends on the energy in the field. But the net product of this, say if with all the motion, any motion in any direction, this electron takes a little bit of energy and kills it. So we have this, I even had this notion that you can't destroy the energy. But in a sense, you can. every piece of matter destroys a little bit of energy from the universe by moving. Because when it does that, it takes a piece of force and slows it down. This piece of force would have been here, okay, if it wasn't for the fact that it had to move this. So the fact is it lost a little bit of energy in the universe. A little bit of time was consumed moving this, which consumed a little bit of the momentum of this object. It's actually moving slower when it has to push the matter, okay, the zero thing. And in losing that little bit of speed, the universe lost a little bit of momentum, and that's actually what causes gravity. So anytime an electron or proton moves, they're consuming force. There's energy being consumed. And obviously if they're moving in all kinds of directions, then they're going to consume force in every direction. And in doing that, they're going to create gravity. They're going to create an absence of energy in every direction. Because every way they moved, they consumed a little bit of force. So you can sort of get it that jiggling, as Feynman would say, does actually consume the momentum of the universe. A little bit of it. And that's all. That's why gravity's a weak force. It's only a little bit, but when you add up a lot of electrons and protons moving, that little bit becomes substantial enough to smush you into the earth. So anyway, very simple. Then obviously you have to add charge to this, and that's where it gets 2 plus 2 plus 2 physics. This would be nice if you could just do 1 plus 1 physics, but the universe actually does have charge, and that has to be accounted for.
So the situation is that the phenomena is probabilistic. It takes odds. It comes down here and has a 4% chance. 1 out of 25 trials. Huh? I think you know what odds are. If you have, for instance, a die, and you want to get a 1 and you roll it, well, it doesn't come out so often, but it comes out sometimes, 1 out of 6.
Right, so, but we know that dice have a mechanical reason. We know we can manipulate that die, and we can, be sneaky, and we can put a funny weight in the die and change the results, and we know it's cause and effect. We know it's a mechanical reason why there's odds. They're not caused by magic.
And what that means, if you roll die 100 times, let's make it 600 times. You roll a die 600 times, you might get 105 ones, or maybe 92 ones, or something like that, right? You get about 100. And if the numbers were bigger, the accuracy in percentage is bigger, not accurate. So,
right, and so the only argument I'm making is that if they thought about the atoms on the surface of the glass, and the fact that there has to be a difference in different locations. Not every location is all electrons, not all locations hit a proton. It's obviously going to have places where there's an electron and places where there's a proton, and those electrons and protons are going to be deeper or more projected, or they're going to be in different locations, and that's the variable that's causing your inconsistency.
If you have 6 billion, no, not 6, 125, 25 billion of these coming down, about 1 billion will come off, okay? Now, let's see, the next feature is, how can it be probable?
So it's 4% off each surface when you're coming down vertically, right? But it does change as you come as an angle. You start to reflect more, a higher percentage. So they're not even accounting for what's causing that effect. But coming straight through, it goes anywhere from 0 to 16. So although the average is 8 for 2 surfaces, so if you're looking through a piece of glass, you got to go through both surfaces. And so it's 4% at each surface. And the question he posed, well, I'll wait till he says it.
Suppose that I had a light so weak that I had only 1 photon coming every few minutes. Will this counter go off, or will the one down here go off? 1 out of 25 times this one goes off. Which time? What determines that?
See, so he says, what determines that? Well, we can say that it's determined by where you actually hit. Whether you hit an electron or whether you hit a proton is going to make a big difference. So we could say right there, that's reason right now to understand why there might be a difference.
Possible theories. Nothing. Pure chance. The world is made of chance. That would mean that the physicists can't predict the future. It would mean that if you set up an experiment with exact conditions, you cannot predict what happens in the future because you can't predict whether it's going to go up or going to go down. You just...
So he's saying it almost like, oh, gee, that's so silly. But he actually is going to say that's the truth. That's what we believe.
It's not 4% odds. Your whole beautiful structure of science is reduced to computing odds. Nature, instead of being definite, does everything by chance. Not so.
So he says here, not so good. But he's saying that's good enough for me.
Other possibility, there are little spots on here. And all it has to, the photon has to hit a spot on the surface. And Newton did several things you'll find out later when I give you more.
See, Newton didn't know about atoms, so Newton, it was pretty clever of him to think that, the surface has got other things on it. And then he figured out how, well, that doesn't work because I still can't figure out how the spots on the top know what the spots on the bottom are doing. But again, he didn't know that atoms actually are connected to each other and that they have to have a geometry. And if they're going to be transparent, they obviously have to have a pretty consistent geometry. And that the bottom surface would know what happened at the top surface. The atoms are a consistent size, and if I move one of the atoms on the surface, the atoms on the bottom surface also have to move.
Phenomena, how these are various explanations, which way it's going to go, and why the spot one doesn't work. But I'll give an argument that Newton made about that. He said it can't be that. Because, he said, you can polish glass. It's wonderful. I love to read these old guys. They knew you could polish glass. But they had the intelligence to deduce from the fact that you can polish glass that there's no spots on it like why.
Yeah. Well, I mean, that's even kind of silly to think that the spots would be permanent. Obviously, you can polish anything. You can rub the surface, you can sand anything. So I think they would know that the surface changes each time you change the surface. So obviously, but the idea would be maybe the spots are indelible. They're in the material. So like vinyl or something, you can sand it, but it won't change color.
What's polishing? See, he polished it. He carved his own lenses. He ground his own lenses. So he knew what it was doing. He takes a coarse grained sand-like stuff with, what do they call it? This
Pumice.
Polishing powder, the grinding powder, and that shapes it, but it cuts fairly obvious grooves. And you take a finer one with finer particles, and you cut the grooves finer, and you make the grooves finer and finer and finer. And after they're fine enough, suddenly it's smooth, and the light comes right through. When it's coarse, it's bounced around. And so he concluded that light cannot...
See, it's not really about the smoothness, okay? It's about the thickness of the glass. So you're really saying that you're really just changing the geometry of the glass. What atoms are up and what atoms are down. And that's all you can do. You're just kind of changing. And say the atoms can rotate a little bit. So they can rotate a little bit this way, a little bit this way. So as you're polishing, you're changing the shape of the atoms in terms of how they look to the world. So if you can polish them all to bend a little bit this way, and then it breaks, the atom breaks, and that one flies off. So you polish the little atom off. But as you're polishing, they can turn a little bit and still do their job. And that's why the reflective index changes as you polish. It just goes through the cycle of you changing which atoms are bent, and then they pop back to center again, and they bend, and then they pop back to center again. So that's your index of reflection, 0 to 16%.
See the grooves. When I polish it, it's not that smooth. It's still bumpy, but on a small scale. Whereas when I have the big grains, it's on a big scale. It can't be any different. When I polish with the small grains, it's just a small scale of regularity. But somehow light doesn't see anything on a small scale. Correct. All experiments have shown that this is absolutely not the right explanation. If it was, there'd be all kinds of ways of testing that. I told you we can measure down to 10 of them.
See, this is nice that he sits there and shows some examples, right? But kind of a debunking of the alternatives. But obviously there's lots more alternatives that you're not debunking. So the fact that you can dispense with some alternatives is sort of straw man, okay? There's no reason for you to think those are the only two possible ways. So he's going to describe another way here. But those are two ways, obviously, and again, neither one of them have anything to do with recognizing that the surface is made out of atoms. So talk about what atoms do when you rub them off of a surface. What do the other atoms do when you rub an atom off the surface? I think they fill in that hole.
Minus 15 centimeters and so forth, and what would happen would be you'd be able to find some area to focus very carefully the light so that the reflection coefficient would be higher than 1 in 25 if you happen to be near a place where there was a spot.
Right, so obviously we can't shoot a photon small as an atom. So if the atoms are the spots, or if the electrons and protons are the spots, we could never have a photon that would hit one of the spots, because we know the photon as a composite object is 2,000 atoms across in one dimension. In one dimension it's incredibly thick, and in the other dimension it's very thin.
Can't do it. No matter what you do, it's 1 in 25. Other possibility, the light that's coming down here, the photons that do it are, well, like footballs. And they spin. And depending upon whether they hit with the nose point or with the flat point, depends on whether they bounce back. In other words, something inside the photon is determining which way it goes. Again, no. Because you can, if that were the case, the light that went through would be all of a certain kind of football.
Right, so that's a good argument for why the light isn't the thing that's creating the variable. So all we're doing is looking for the variable. This is like rolling the dice. We're saying, why are the dice coming up different ways? And we're saying, what are the possible things that are causing it? Where are the variables? Well, the idea is that there's ways to know the variable can't be in the light, and the variable has to be in the surface.
And if you try the reflection again, you'd expect a different number than 4%, because of the fact that they're all lined up, and you can't line light up. You can't fiddle around up here by any kind of filtering that'll change that percentage. All the light.
Right, but you can by just polishing the glass. So again, we have an obvious mechanical change you make that changes the glass, and you get a different reflective index. And he's saying that's random. Well, how is it random? You clearly know that polishing the glass is the cause. You know that you're changing the glass when you're polishing it, so that's clearly the variable that's causing the effect. So why do we have to think it's random? When we know you're changing the physical circumstance. See, it's not random like you shoot the light in and it goes from, it just says 4% now, and then a minute later it says, no, it's 16%, and then a minute later it says, 9%. It's not varying by no reason. It's varying because you polished the glass, and he's just basically saying polishing doesn't change it. Well, of course it changes it. And it changes it through a cycle of, as I pointed out, you make atoms crooked, they break off. It's like how much you can bend a tree branch and then it snaps. And it's, they're all kind of the same. You can bend it this much and then it breaks, and then you bend it this much and it breaks.
Photons are identical if they're the same color, as in one color. They're all identical, and they behave with 4%. Are we therefore reduced to this horror that physics has got reduced not to these wonderful predictions, but to probabilities? Yes, we have.
So that's it. So he just said it right out in front. It's magic. There's no cause and effect. The universe resets everything. Somehow I can't make the same conditions and rerun an experiment and get the same results, because there's never the same. The universe randomizes differently. So no matter no matter what I set the glass at, no matter where I polish it, somehow it's not going to do exactly what I just polished it to do. And of course it is. So this is this is almost ironic in the sense that he knows that we can actually calculate how thick the glass is and actually polish it to that thickness and know exactly how much reflection there's going to be. Apparently you do it for submarines, right? So, with submarines we have to look out the glass and you have all that light on the inside and it's really dark on the outside, and they want to stop the reflections. So they actually know that they just polish the glass and they can get the reflective index way down.
The situation today, in spite of the fact that philosophers have said.
So again, it's this line he gave in the other video, and I'm just saying, to reasonable people, this sounds like religion, right? This is the argument against religion, and he's basically mocking it.
There's a necessary requirement for science that setting up an experiment exactly similar will produce results exactly the same the second time. Not at all.
So he's saying not at all. He's saying I can't set up the same results and I'm in the same conditions to get the same results. He's saying somehow the same conditions can create variable results. And he doesn't have any evidence of that. That's a rather bold statement, right? And it's just let go, like somehow you can make that kind of bold claim And you don't have to prove it with anything called evidence, anything called good evidence. He has no good evidence that on a nuclear scale you can't create exactly the same conditions and get exactly the same outcome. And even on a plane scale, like I said, it's already known that I can calculate at an exact distance the thickness of the glass, and if I always make the glass that thick, it'll always reflect this much.
1 out of 25.
Because the atoms are always the same size, and they're always doing the same thing. I mean, obviously, if I change the material glass, if I make the glass out of, put more lead in it or do some other thing, then yeah, it's going to be a different number. The thickness will be, the thickness that causes zero reflection will be a different thickness.
Up and sometimes it goes down, unpredictable, completely by chance.
So again, he said, and no, it's completely not by chance. It's completely by how much atoms I rip off the surface.
All right, I already see you turning off. I can see you say you don't understand me. You can't understand that it could be chance. I don't like it. Tough.
So that's the famous, you don't like it, tough.
I don't like it either, but that's
Okay, he does like it. So, he says in later that, oh yeah, I didn't mean to say I don't like it. No, I'll accept anything. Go ahead, stick anything up my butt, and I'll eat it. I'll take it. I mean, that's all he's saying. He said, I'll believe anything. I'm gullible. Go ahead, hit me with any kind of bullshit.
the way it is, okay? I don't know.
That's the way it is. That's what he said. It's not the way it looks. It's not the way the evidence actually looks. So why should I believe it? This experiment surely doesn't prove it.
I don't understand it either. I don't understand it. It must be that nature knows whether it's going to go up or down. No, it is.
Nature doesn't know nothing. So this isn't about nature. We're talking about circumstances and that atoms have behaviors. And you're saying that atoms can modify their behavior, that they have some kind of control, that somehow the little bits are going to decide to be here instead of here and reflect instead of not reflect by some sort of bullshit. And there's no evidence for it. Again, we have no vision. We can't see these tiny little things. We have no idea what they're exactly doing, and yet they make this bold claim.
Not be that nature knows. We are not to tell nature what she's going to be. That's what.
Yes, we aren't to just make up things, and you just made up something. So you have a principle. Don't make up crap that's just crap, and you just did it.
We found out. Every time we take a guess at how she's got to be, and go and measure, she's clever. She's always got better imagination than we have.
Right, but that's not the truth either, right? So our science has done pretty well. We have found lots of things that are durable truths. We don't get tricked by nature. We put the right fossil on the right head, on the right fossil, and do all the things right, and it comes out right, and we have a nice, good, solid piece of information. Not all of our information is sloppy, stupid, and messy.
And she finds a cleverer way to do it than we have thought of. And in this particular case, the clever way to do it is by probability.
So again, by probability. No, it's not the clever way of doing anything. Unless you want to calculate some stupid thing. Unless you want to know how thick I got to make the glass to make it reflect zero. Otherwise, understanding it is completely different than utilizing it. Utilizing information is different than understanding it. So understanding why the light reflects, he didn't enlighten you at all. And he basically just said, forget about thinking about it, just assume it's magic. That's what he just said. The best physics can do for you is we'll just call it magic and let's just have fun doing math equations. That's not understanding anything. That's just using it.
Why not? And so the first aspect I have to tell you about then is that light works by probability.
So it really doesn't. It works by the same way everything else works, by cause and effect. And there's no reason to doubt that. No good reason to doubt that there's causes that cause the light to reflect and causes that cause the light to transmit. Physical causes.
All right? By the way, just incidentally, the wave theory had no difficulty with this at all. Because what happened was...
See, he discounts the wave theory, so he just... He has no difficulty, but waves aren't real, so fuck that. It is kind of funny. He says, waves work, but screw that. I don't like waves. I don't either, but, frankly, but it's another argument where I would like to say, look, Feynman says, but it's no point because it's not true. It's not a good argument.
Like the waves or something are coming down here, and they shake, and they just keep going, but some of them bounce back. Something like a sandbar sometimes partially reflects the waves in the sea. So some of the energy went back. But waves don't operate this thing. By the way, when you turn the light on...
So he's basically saying, see, waves don't work for any measurement device. It's just going to find a tiny bit of energy hits, and it shoots an electron again. But again, it's still a clump detector. A half a clump won't push the electron, but it doesn't mean that the half a clump didn't hit the detector.
This might go off at any moment. You don't have to wait for a certain length of time. Of course, there's odds that it goes off at any instant, but it could accidentally go off the moment you open the slit. So it's not a question of waiting for the energy of the wave to pile up or anything. It's hopeless. I have to start with light as particles.
So he just said, light as particles. Light as particles. So just understand, this is physics that's supposed to be written in stone somewhere, and the physicists can't get even this right. One will assert just as vehemently that light is a wave. He just asserted it's a particle. Who's right?
Waves explain many things, but not right. It's particles, okay? It's photons. The problem is they're reflected with probability.
No, they're not reflected with probability. I mean, there's a probability created by the variables. Just like rolling dice, the things you hit will cause the dice to turn and create the outcome, the probabilistic outcome, but it's not being created by magic.
Now the next feature, having to do with reflection again, that I would like to describe is something that you're also familiar with, perhaps not so directly, but perhaps you've seen the colors in soap bubbles. It's made out of soap water, which has no color. No color, I've seen the color. Mix it together, get a lot of soap water together and look at it. No color. You take oil, which is a sort of a yellow fluid, and you drip with blackish yellow junk. It drips out of an automobile on a rainy day. You must have experience here with that. And you look at the puddle, to your delight, there are colors. Colors. These colors are produced by reflections from two surfaces near each other, very close together. If the surfaces are far apart, we'll discuss it later, the same phenomenon really occurs, but it's much harder to see under normal circumstances.
You can't see it because the further apart they are, the smaller the little lines get. Okay, so this is the thin film interference pattern, but again, it's not interference. It's just constructive reconstruction again. You either put a photon back together or you don't. If they're out of phase, you can't put the pieces together. So if you have photons hitting something, all right, and you send them to locations, obviously if they're difference in distance, so these two got shot over here, you could say, the pieces. If their difference in distance isn't one wavelength amount of time, then they won't be able to meet here in the proper sequence to create a photon. They'll lose their frequency information. Okay. So the pieces get off here, and so these two pieces were in the same time, but the point is that the distance difference will mean that one will show up first and one will show up second. So this one will be 1 and this will be number 2 here, right? 1 and 2. Well, this would be 1 and this would be 2. So you're recreating a photon by sending two pieces from different distances. And likewise, you can do the same thing where, the first piece is the longer piece that takes the longer distance, and the second piece comes from this one, and so you have the time again. But it's just about reconstructing the phase. Obviously, if this distance is another half of wavelength, well, then this one will show up at the wrong time, and this distance will be too far or too close, and it won't be recognized as a photon anymore. It won't be received by the electrons. Okay, more than one has to be hit, and the key point is that for every wavelength of light, the polarization, as you get smaller wavelengths, if you get higher frequencies, you get less and less polarization, which means the light hits a smaller and smaller surface. And so that's part of why you don't end up making blue light out of red light, is because the red light is spread over too large a surface. So even though it's making blue light, in the sense that it's sending the energy there and hitting some electrons, it's hitting electrons that are too far away from each other. And so the impact on the atoms isn't what you need to create electricity. So it doesn't create a signal. But it did arrive there. So the point is that light goes everywhere. So the light comes in as a bunch of quanta, in all kinds of arrangements, all kinds of amounts of it. And there's just places where there's more density of it and less density of it. So there's more little bits in this little section and less little bits here, more and less, and it hits, and that's interpreted into photons on every surface. And it's just the ones that produce the right sequence that are called a photon, and the rest of the energy is just energy. It's just going to heat the object. It won't create an electrical signal that you call a photon. So anyway, so in the thin film, the idea is again that you have a thin film, part of the light's going to reflect, all right, and then part of the light is going to reflect a second time, okay, come out, and then it's going to reflect a third time and come out. So there's light coming out at all these points of reflection, and the points of reflection have to do with this angle, and that makes this angle, which means how far apart these little things are. So the further apart I put the surfaces, the angle gets tighter and tighter, okay. So you can sort of understand that as the angle gets tighter and tighter, more up and down, more vertical, that the bars get thinner and thinner and thinner, closer and closer and closer together, and that's why you don't see them once the film gets a certain height. So it has to be really thin for there to be enough separation to create bars you can see. So the thinner you can make it, the wider the bars are. So when you see the bars, they'll be further apart depending on how thin the film is, and so then you can see them. And if I make the bars smaller and smaller and smaller and smaller and smaller, obviously there's a point where they just blend into each other because there's just tiny, 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 tiny. It's like the pixels on the screen of your monitor. You don't see them, but they're individual little pixels, and they would make a little bar pattern if you looked at it close up. All right. I think that's enough of that. I think that'll do. I think.
What happens there is that in a soap bubble, for example, there's a layer of water. And so we have two surfaces at some distance from one another. So, and then the photon could either come down here and reflect right away, or it can come down this way and reflect from back there. Okay? Now, as it turns out,
you can sort of understand that the refraction, that is, when it goes into the stuff, it refracts, and that's changing the angle. And the smaller the surface, the less angle. That's probably the wrong way to say it. The thickness of the surface. Well, anyway. No, it's really just the amount of time it spends. The thinness just changes how many times it bounces, and you can sort of understand that. It bounces more times in less space, the thinner the material.
that is about the same percent. If it's just
Still said that wrong.
water between air and air, it's about the same 1 in 25 both times. What's the color? If I'm going to do it with monochromatic, like a light of one color, what can you see in colors? What you see on an oil film, on a mud puddle, or in a soap bubble, when you use light of exactly one color, is not colors, but bands, bright and dark bands. Places where the light is reflected very well, and places where it's not reflected at all.
Right, so if you're basically just saying that you have more than one interference pattern. So each frequency of light creates places where you have this constructive reconstruction. And the fact is that each color is in a different location. So they mix because they slide over each other. So one band is on top of another band. So you have this red band is here, the blue band is a little here. So you have a little bit of blue and a little bit of red in the same place. They have an overlap. And then there's a little bit of yellow over here that's overlapping. And that's where you're getting the colors from, is the overlaps of where the photons constructively reconstruct.
Across the bubble. Now, the position of those bands, if you first look at a bubble with red light, you see bands, black and red bands all over. You look at it with blue light, you also see blue and black bands. But the pattern is not the same. They're displaced from where the red ones were. And so when you have both red and blue, you get purple and red and black and purple and so on. Now, if you add to that yellow with its pattern and so forth, you get all these colors mixing, okay? So we want to simplify experimentally.
So with each thickness, there'd be a different kind of overlap. So if the thickness is the same, then you have the same amount of, you'll have 70% red and 30% blue, and so you get purple or whatever.
As Newton did. And look at these, this reflection. What Newton, most of his experiments he did this clever way. He had a beautiful curved piece of glass, which was a lens, and a flat piece, and put them next to each other. And then this was only a very slight curvature. And so
right, so that's the key. So he kind of overdraws it, and it kind of gives you the wrong impression. But, you know, you wouldn't even see the curve. It's such a slight curve.
He had this gap between the two. And when he shone light this way and looked at reflected light, which, depending on where you looked, see, this is a cross-section of the lens, which was more completely like that. There is some reflection in here, which is irrelevant at the moment. There's another glass plate down here. When he looked in different places, the light came down all over. And when he looked in different places, he was looking at...
See, these distances, the difference in these distances is the size of a grain of sand or smaller. Anything bigger than that, you won't see the pattern. So, I mean, it's really small distance. Half the size of a grain of sand. I mean, it's really... We're talking about dust. We're talking about that kind of thickness. A piece of dust.
Cases that corresponded to reflection with one gap or another gap between the sides. And when you looked at this with monochromatic light, looked down on it, since it was a spherical lens, you saw in what I call bands in the soap bubble, but more organized, you saw rings, called Newton's rings, with a black area starting and then red. If it was red light he was using, and black.
Right, so that's the bullseye pattern, and obviously it's behind his podium, which isn't too great, but anyway, that's the interferometer pattern.
And so forth.
Clue. You know.
These looked like they were coming closer and closer together, but he was a clever man and understood immediately what it meant. If he measured the distance from here to here, and plotted the answer for whether it's red or dark against this distance, not against this, instead of measuring away from this.
So the bands clearly got thinner and thinner and thinner as you went out, because the thickness is getting thicker and thicker and thicker, so the difference, the size of the bands is getting smaller and smaller. So just like the slit experiments, you change the size of them by changing the distance the light travels at its frequency.
He measured how far apart these plates were. Then he found, like our friends the Mayans, every time you had 365 pulses, they got black. In other words, if this was black and this was red, then double that distance was black again, and triple the distance was red, and 4 times the distance was black, and 5 times the distance was red, and so on, nice and even. In other words, instead of measuring by this distance, by measuring the thickness, you find the following experimental result. Reflection coefficient against thickness between the two layers. Okay? The spacing between, in this case, if it's an oil film bubble, with that's the distance. In this case, it's the spacing between the lens and the plate. And if you could change it, it's harder to change it, a soap bubble under control, but it changes automatically as it dries out. You get the following. You get no reflection if the thickness is 0, then you get a strong reflection for a certain thickness, and then if you make it thick, you get no reflection, you get a reflection, then you get no reflection, you get no reflection, and so on and so on and on. And now it's getting thicker and thicker. Does this go on forever? Yep.
So he's just talking about the fact that, you know, it's a reoccurring pattern. That obviously what you're doing is in multiples of a wavelength. I mean, you're making the thickness of the glass a wavelength thicker, so you're changing when they're going to be in phase and out of phase. So you're not really changing whether there is a reflection or not a reflection. You're just changing whether the thickness is the same as a half wavelength or a full wavelength. A half wavelength difference in the distance, and it's destructive in the sense the pieces won't be in the right distance from each other. You won't recreate a photon. You'll create 2 radio signals out of phase, and obviously it won't show up as a radio signal because it's two signals hitting the same thing out of phase. But obviously it's not the same thing as that. I'm just using that as an example because of the radar experiment and all that kind of crap. But the idea is the phase is the only thing that's important here. So that curve just says, obviously you're a little bit out of phase, a little bit out of phase. Okay, now you're in phase, perfectly in phase. Now you're a little out of phase, a little out of phase, a lot out of phase, opposite phases essentially. A little bit, that's all it's saying. And that reoccurs. Of course it reoccurs. The number of, dividing 3 into 9, it's like a reoccurrence, okay? So you could say, I just make the 9 as big as I want. I can just go 3, 3, 3, 3, Come on, not complicated. How many multiples of the wavelength? And if it's a uneven multiple, if you have a remainder, then you're going to be somewhat dark.
If you got good enough monochromatic light and get the experiment under control, you can make it go almost indefinite. You can make this work for distances of 1 meter or more.
So he's really talking about you can make it work in the sense that you can make, shining light through even a piece of glass that's 1 meter thick. And the polishing thing still works.
Still, keeping track whether it's even, odd, bump, bump, bump. Okay? There's nothing that's interesting. Very interesting. But that's damning. Why? Because what theory were you figuring for the reflection from that? That made the reflection be 4%. The odds, 4%, whatever. You put another layer down here at the right thickness, expecting to get 8%, and you get nothing. How does the layer down here turn off the reflection from the layer up here? Right. So that never happens. It never turns it off. The total thickness tells you what the total reflective index will be. They don't tell each other what to do. The fact is, though, simply is that when you change the top surface, you change the bottom surface. The atoms are moving. They don't, if I'm an atom and there's another atom and there's another atom, that atom can't move. That one can't blow up or disappear without me or the other guy filling that void. There's no empty spaces in the glass, so to speak. There's no vacuum space where there's no atoms or something. Yeah, there can be other compounds, but there's no absence of atom thing. Well, there can be bubbles, but again, that's, those are atmosphere. But those are, again, surfaces. So yes, at the surfaces you can have atom and then no atom, obviously. The glass atoms stop here and then the world starts, some other material starts somewhere else. So obviously if there's a surface inside the material, then yes, those atoms won't fill that void. But the point is that the atoms of the material clearly don't allow the other atoms to move without them moving too. Or if you figure that out, and you make the layer just a little thicker, it doesn't turn it off, but in fact the reflection is more than twice.
Right, so it's really, look, I'm just saying, I've sort of explained this before, but I haven't done it for a while. I mean, you can just sort of understand it a simple way. Just take atoms and draw them. Okay, so you just draw a surface, or just draw the atoms. You draw the atoms. Okay, and let's say the atoms have some shape to them. Okay, so let's draw them as a little bit oblong. All right, and then you could just understand that. Okay, that fits inside of a surface. But if I make the surface a little smaller, okay, then you can sort of understand that these atoms don't fit anymore. So if they don't do something like this, right, they can't fit inside the surface. So they have to change their shape. They have to change what they're doing. And so you could argue this is 0%, and the more they turn, the more this will be, 4%, and this will be 8%. Okay, and then there's a point where they can't turn anymore because it'll break down the structure of the material, so they won't turn anymore. So that atom goes, and now they can fit again, being this way. So instead of 4 atoms, it'll be 3 atoms. If I make the distance here, then 3 atoms can fit. but that's all that's happening. You're just compressing the atoms, and as you compress the atoms, you distort their shape, and as you distort their shape, you distort how much light reflects. It's a simple explanation that works.
On this scale here, this line would have been what you would have expected if you expected it always to be 4% plus 4% or 8% from the two surfaces. This is what you would have got if you disregarded all this nonsense that actually happened. By common sense, it reflects with a certain odds, and it reflects with a certain odds, and so altogether you get twice as many coming back. This is the twice as many. But for some, if the thickness is 0,
so you wouldn't expect it if you knew that you polish the glass, you change the reflective index. So we know it never acts like that normal case. It's always, okay, it can be 4% and 4%, but it's only one thickness that'll produce that. I mean, one wavelength difference in thickness that produces that. So again, this is just the change in the thickness of the glass is related probably to the size of the atoms. So you could probably just say it correlates. So the amount that you're polishing off per cycle is just an atom's worth of distance. So for every atom's worth of thickness in the change in the surface, you go through the whole cycle of 0 to 16. And then when you're a full atom, then you go back to 0 again. And then you go to 16, and then you lose an atom, and then you go back to, and you're just repeating the same cycle of polishing off an atom's worth.
Don't get anything. If the thickness, hey, that's not such a bad idea, is it? If you don't have any water there at all, you wouldn't get any reflection. Starts out right anyway. So that theory was kind of dumb now that I come to think of it. And that helps to explain Newton's observation when the distance is too small, the light doesn't know anything about it. If the thickness is sufficiently small, it doesn't reflect. It does exactly the same as if there's nothing there.
All right, well, that I don't even know if that's true. So if it's sufficiently small, like no atoms fit in it, yeah, then you can't change the atoms. If there's no atoms, then there's no thickness and blah, blah, blah. I mean, there's just nothing to reflect.
But the horror of it is, it's all right that it increases as the thickness goes up, but it overshoots, you see. And then it comes back to 0 again when the thickness is just right. It's very difficult to invent a probability thing. If I have these spots on this surface, it's very hard to see how you're going to have spots on this surface, which turns the spots on that surface off when they're the right distance away.
So, but it is very easy to think that atoms fit inside of packages. And if you change the size of the package, the atoms move to fill the package.
And so Newton went a little bit nutty. And he talked about fits of reflection and transmission and so forth. And I would like to now just finish this by telling you what is the answer. Now, here's the answer. This is the way we figure this out.
All right, he didn't figure anything out, okay? All he's going to do is tell you how to do probability, statistical math. So he's going to tell you how to add two variables. So you have two variables that are causing an effect, an outcome. So you have two events that cause an outcome. And he's just going to tell you how to add the two probabilities. The probability of the first event doing it and the probability of the second event changing it. And so he's just going to tell you how to add two probabilities. That's it. There's nothing, this is just statistical math. It has nothing to do with understanding or physics. It just has to do with an easy way to understand. This is a recurring cycle, right? So this clock thing only works for patterns. It only works for things that do go through cycles, that go from, like where you're doing this half a wavelength difference, full wavelength difference, half a wavelength difference, full wavelength. So anything that has a cycle. And so he's going to represent time with a clock, and time is just distance. So he's going to talk about just turn the clock. So you have your first event, which he's going to give a 0. He's not going to define the first event. So he says there's two surfaces, there's two events. He's not going to give the first event any meaning. He's just going to create an arbitrary first event, and then just say how much time passed means how much more distance passed. That means, so he's just now calculating how thick is the glass. Okay, so he says here's the 0 point. Okay, there's your first event. Now I'm just going to calculate with this clock how long it took to get to the second event. And that'll tell me the distance of the glass, and that'll tell me what the total reflective index is now of that glass. And it's going to just basically say, what am I going to get, 8% or 9% or 10% or whatever the percentage will be decided by the thickness. So this is just a way of using time to tell you distance. And you're really just saying there's two events to the distance. The distance has the A and it has B. It has point A and point B and the distance. So this math is telling you nothing that you couldn't know just by knowing the distance. And if you know how big the atoms are, right, you just divide the distance by the size of the atoms, okay, atom size, and you know whether you have a full atom or a, you know if you have a remainder. So if the distance is 10, and I know the atoms are 1, let's make it a number that's odd. So we know the atoms are 3. I know 3 doesn't go into 10, so I have a remainder. So I know I'm a little bit off of a full wavelength or a full atom. And so I'm just going to get that remainder and say it's a 1, which is kind of small, 1. So it's going to be a little less than bright because it's a little bit off. And just the higher that remainder is, the more, okay, so if it's 11, the remainder goes up higher. And so the closer I get to a bigger number like 3, so anything getting close to the number 3, like 2.9, I know that's where it's going to be really dark. That kind of thing. That's all this is. So it's just a cycle. You reoccur. So as you go through, as this number increases, this number gets closer to 12, let's say, where it goes back into it evenly again, and then it goes uneven, uneven, uneven until it gets to 15, where it goes back to being even, a whole number again. So that's all he's calculating. It's nothing. There's just nothing to this. He's doing statistical math. He's found a shortcut to do statistical math, to sit there and add probabilities. But he's not even technically adding probabilities. He's just defining a distance with using time.
It goes as follows. What we're going to calculate is a probability. The probability of a particular question. And then a probability that this counter goes off. The probability that if I had one photon coming down.
Total reflection. See, so one photon obviously wouldn't work because the one photon isn't going to be able to play the game right? It's the single photon can't possibly give you the representative result, I don't think. Well, regardless, the point is he's calculating the total reflection. That is the reflection off both surfaces. So that's the key to understanding this. He's not telling you what the first surface does.
It'll come back to this count.
He's just telling you after it went to both surfaces what happened. Now, obviously, if the single photon bounces off the first surface, you can't have any probability of it bouncing off the second. So there seems to be some limitation to this idea of doing it with a single photon. Because a single photon never has the opportunity, when it hits the first surface and reflects.
And here's the way the rule is for finding the probability. Now listen, hold your seats now, hold on. Don't be afraid, just go along, all right? Never mind if you don't like it, huh? Just hold on. It works like this. What you do is you take a piece of paper. A piece of paper has nothing to do with the original thing. The piece of paper is only make marks on. It's got nothing to do with the light, all right? And I have your following rules. That you make an arrow to represent, well, for each reflection, you make an arrow. This arrow, for example, is for the reflection from the front surface, and this arrow might be the reflection from the back surface. And I'll tell you in a minute how to make those arrows. And then what you do is you tie the arrows together this way. You make one and then the other.
So what he's not doing is pointing out that the total probability would be those two arrows end in a straight line. So what the total probability is that radius, and so that number, whatever that radius would create as an area of a circle, that's the 100%. And now he's just calculating how much you're off of that 100%. In that, at what distances are the arrows the least in the same direction? And that'll be destructive. Constructive will be the arrows in the same direction. Destructive will be the arrows in opposite directions. And everything in between will just be some percentage of that.
All right? That means you make this arrow and you put the tail of the other one on the head of that one. There's the first arrow is a reflecting arrow from the first surface. And this is the second arrow is the reflecting arrow for the second surface. And you put these two arrows together by this rule. And then look at how far off you've come to the end, yes? Yes. You count the pins in the hole. You count the number of beans you put in the barrel. I mean, you make these pictures. And then you ask, how big is the circle? In area. That area represents the probability.
So it's just something like Pythagorean square theory, you know, where you're just taking the square of the distance, and the area is the hypotenuse is a little bit different than the two sides added up.
That you get the thing back. If the circle area is big, then you get a high probability. If the circle area is small, you get a small probability. I just have to say one more thing on how to make the arrows. Answer. Well, the size of the arrow depends upon the particular materials. I won't come into that right now. The absolute size, 4%, is another matter. What you do is you make an arrow, and depending upon the time it takes for the light to get from the source where it started to the place where you want to count it, you turn that arrow like a clock, depending on how much time. So if it takes a long time, so you start out at the source, there's the arrow.
They both have the same origin, right? So they both came from the same place. So this part, that time, was going to be equal for both of them. So that part doesn't mean anything. The second one has to travel the same path as the first one in terms of this part. So what he's really just saying is you just take an arbitrary first arrow, okay, accounting for that distance, and now you just measure the new distance, the extra distance the second photon travels. So just measure the extra distance to get to the second surface, and that's all you're doing, is showing the difference between. That's the only difference that matters. The other difference is exactly the same for both arrows. All that spinning was exactly the same, so you just ignore that.
For the source, but that's not the arrow you're going to draw. That's just thinking. And then you say, turn over, ding, 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 round, depending on how much time it takes. At a certain rate, every second it goes around 75,000, goes around a hell of a lot of time. It goes around 1 followed by 15 zeros. Time, in 1 second. It doesn't take light very long to get to the source.
So I don't think that's accurate, actually. I think that's light in free space, but whatever. So I think he meant to say half of that, or 40% of that.
It still turns around a lot of time. You turn it around, okay? It's like the roulette wheel, and then just at the moment it hits the counter, it happens to be sitting at some angle. All right? And that's for the reflecting from the first circuit. Now, what about, that was supposed to be this one. I've gotten too many arrows on here. What happened is you take the first surface reflection, turn it through at this angle depending upon the time, and it ends up here. See, that's not very...
Right, so you're just saying the first surface and the second surface have the same origin. So you just think of both the arrows in the same place, and now on top of each other. And now the second arrow, you're going to do its difference, and its difference is the only difference that matters. The time it takes to get through the material to get to the bottom surface is the only time that matters. And again, he's just calculating the distance. So he's just establishing the distance.
Big angle. You said it was a big angle. It is a big angle. You know, if you keep on turning, it can look like a small angle when you're done, but you had to turn around, right? You know what I mean? It goes around like a clock hand. After 25 years, it's still saying 2. It can start at 2 and end up at 2:15. That's 25 years. It went around. So here it is, having been turned around a lot of time. Okay, this is from the first surface, I should say. That's the one, the arrow for the first.
And so for each time it's going around, each time it goes around, it's just calculating one atom. How thick is one atom? So one atom is one turn. One atom is one turn. One atom is one turn. And so it's really just telling you, when do I have a half an atom? When do I have a quarter of an atom? When do I have, we're just talking about the distance and how many atoms can fit in the distance.
Second surface, rule. Same as the arrow for the first surface, but in the other direction. It's just an accident. It happens to be the opposite direction it starts because, well, not because. The rule will turn out later. When you go from air to glass, it's one way. From going glass to air, you change it, huh? Anyway,
so he's just stating that when you're going into the material, you're going into a denser material. When you're reflecting off the bottom surface, you're going into a lighter material, so there's no phase shift.
This way, for the second surface, and you turn this one. No, which way did I turn? Yes. For the time. And when you get finished with this roulette wheel and the second one, it comes out so. And then you add them together the way I said. You tie one on the other end and make the set. And that's the laws of electric light. And that'll tell you whether it reflects or it doesn't reflect. And what difference does it make? Why do I get these ups and downs? Well, sure, if you move this, kept that the same and move that, what is that going to do to my exercise over here?
So the simple way to explain it is just to put beans between two surfaces and just see when you compress them how the beans have to turn, to accept the compression. The same thing's happening with glass. To accept being compressed before they get ripped off, the atoms have to change, and the change in the shape of the atoms, or the orientation of the atoms, however you want to say that, where the electrons are and where the protons are, is changing. The fence is now changing, which is changing the reflective index. You're changing. If the fence, you can sort of understand, if I made a fence with a bunch of thick rails, you can understand that as I turn the rails, I make it really easy for light one way and really hard for light the other way, right? Against the rails, I'm always going to hit the rail. I'll never get through the material. But as the rails turn, I can go straight through really easy. So, you can understand it as louvers even. As the atoms turn, they louver the environment. So now the louvers are changing, and so now it matters what angle you're coming in at.
Answer. The first arrow, the time doesn't depend upon where the other surface is, so it does exactly as I did before. I'm doing the same experiment with the bottom surface a little further along, okay? Top's the same place. Now the second one, however, when I went to turn it, it's a little bit further. It takes a little longer to get there, and therefore it's turned to a new position. So this second...
Right, so it's just representing, again, what's the significance of this time thing? Its only significance is you've just measured how thick the glass is, and that's all you did. You just measured the hard way how thick the glass is.
Time, the picture would look, if the thing was thicker, the picture might look like this. Instead of being here, since it had to turn further, perhaps it turned to here the second time. And then when
we kind of obviously can't measure the thickness, to an atom's worth. So we can't do this, we can't just measure the thickness. So having some abstract way to model it is fine. But this is very abstract from the reality. The reality is you're just changing how much space the atoms can occupy. And by doing that, you change the reflective index. That's the variable that changes the reflective index. And the bottom surface knows exactly what happens at the top surface.
Add these two things together and tie one on the end of the other, and I just do that again here. You see that this line is now a long line, whereas before it was a relatively short line. This, remember, was the answer line. The answer line is a longer line, and the area here is much bigger of this circle, and the probability is larger. And this upping and downing is and the answer just comes out exactly predictable just by this little game.
Right, so this little game doesn't mean anything. I can find lots of circumstances, like the two slit, you make them a little bit wider, a little bit wider, a little bit wider, right? If I make this surface a little tiny bit wider, a little tiny bit wider, I'll have the same reoccurring pattern, except the bars you create a new bar, new bar, new bar, so the bars get smaller and smaller and smaller. But it's the same reoccurring cycle in that you're just changing a wavelength difference. So this math would work. It would work for lots of things that have a pattern, but things that don't have a pattern, it's useless.
That's a shock, huh? You say, yeah, he's going to explain why it's like that. That's exactly what I'm not going to explain. I don't understand it. That's the way it works.
Right. So again, it seems like he's answering the question of why, and he's not even coming close. He's just giving you a statistical tool to define a distance using time. And that's it. It's nothing. It has nothing to do with understanding why photons reflect.
What I'm going to do in the next lectures is to tell you sort of the generalization of this. This is a special example for reflection. I'm going to tell you how the rules go about turning arrows.
So again, it's not a generalization. You can't get more general than this already was. This was already an abstraction, and now he's going to double abstract. That's all. It doesn't get any closer to the truth. It just gets further away from the truth. It gets further away from answering the question, why? Why? Why do photons transmit and reflect? What mechanism causes the two different actions?
It's in fact somewhat simpler than this example. It's not bad at all. It's easy. It's not hard, but much more generally. And what I've done is this is a prototype of the general result. There is no secret behind it. that we can do any better than give you that result. All I'm going to do is generalize it. It's going to sound something like this. This part you needn't understand right away. It's what I'm going to elucidate in the next lecture. The idea goes as follows, in general, which is a statement, and I'll come back and do it again, so don't worry. To calculate the probability of an event, which can happen in a number of different ways, the probability of an event is always what we call the square of an amplitude. Walk in this model, it means the size of a circle corresponding to an arrow. An arrow is called an amplitude. For every event, you calculate an amplitude, which is an arrow on a plane. The probability is the area corresponding to that arrow. All right, that's the first thing. Second.
Right, so it's just a way of doing statistics. So you're just measuring statistically the difference between two events, and you're doing a product. You're minusing one event, the first surface, from the second event at this different location that we know has a consequence on the reflective index. So as we change the distance, we change the location, and we're just using time to measure the distance, to account for the distance.
And how do we calculate the amplitude for an event? If the event is simply a photon going from point to point to another of a definite color, then it's simply an arrow which turns depending on the time. And that's the amplitude. Notice, by the way, if there's no reflections and no trouble, it just turns, the area stays the same, the probability of finding the photon is not altered. And even though the arrow alters, its area is the same. It's when we get in trouble, when we have more than one way to occur, then the rule goes as follows. If the thing can happen in more than one way, then you find the amplitude. What that was, the arrow, for each way. See, if it could happen in two ways, you get the arrow one way, and the arrow the other way. And if it can happen three ways, if it was a double layer of stuff and so on, then you put another arrow for the third way. Maybe that was a short one. And if there's a fourth way, you put another arrow. And when you're all finished, you put them tail to tail, all the possibilities, and find the total, what we call the total, or the net result of making all these little arrow steps. And that final arrow is a total amplitude, we say, for the event to occur. The probability is, as always, the area corresponding to that arrow. Now, that's kind of stinky, right? Well, it's
right. So it's just saying what's the probability of them being in phase. And the more out of alignment they are, the less probable they're going to be in phase, and the smaller your area is going to be. That's really all it's saying, is what's the probability of them in phase.
fun, and it's strange that nature's like that. And I hope you come back to hear how it works in general, a little bit better statement of this to review it. And one other thing, I am going to try to explain to you how this rule explains several of the ordinary phenomena that you're used to in life.
So it doesn't explain any of them. It's just probability statistics. It's a mathematical gimmick. It isn't anything to do with explaining why.
Such as angle of incidence equals angle of reflection. On reflection, that light bends as it goes from air to water, and it travels in straight lines from point to point, and so on. It's all hidden in that one rule. And how that one rule
never explains any of that.
Carries all this information as part of the next lecture, as well as I would tell you right away, one more thing, that this rule, that to figure out what happens in nature, you have to calculate an amplitude. It's not just for light. It doesn't make any difference what happens. An electron does something. A nucleus explodes. Doesn't make any difference. How do you find it? You can only calculate the probability it's going to happen. And how do you do that? You can guess. You calculate an amplitude. That's a lousy little arrow. And the probability is the square of the amplitude, we call it. That's really deep.
And the only way it works, though, is you have to have some kind of confined variable. We know that there's just one thing that causes the effect, changing the distance between the two surfaces. That's the only variable. Now, if there were other variables that are changing the effect, he can't, he's done. He's cooked. He's finished calculating anything.
Causing, in our case, the circle of the amplitude. The circle that measures the probability.
Obviously, with dice, there's more than one thing causing the effect. The momentum of the dice is constantly changing. There's no constants. You know, the fewer constants you have, the less hope you have of doing this. So again, this only works if you can narrow the constants, if you can narrow the variables. It only works if you have a narrow variable.
And that's true not just of light, but of the whole structure of nature as far as we can tell. And although quantum electrodynamics is only about electrons and light, we've discovered that part of the rule, at least, is valid also for nuclei, nuclear particles, quarks, and everything else. The thing that is...
Yeah, all that crap doesn't exist. And yes, of course, there's patterns in all kinds of places. And so there's places where this will work, where there's patterns. And again, the patterns usually just have to do with the fact that things come in clumps. And, you know, clumps of frequency, clumps of clumps. You have to remove the clump or not remove the clump.
special about electrical dynamics is our complete knowledge of exactly what the rules are for drawing the arrows. But the fact that you have to draw arrows and end up calculating probabilities like that, which is such a shocking and horrible form for nature, is something that I will talk about next time in further detail. Thank you very much.
Complete crap. Okay, questions are
These
the good part.
rotating arrows are all very well, but is there another model?
The question is there another model? Naturally, we struggle to find it. I'll tell you the answer.
So this isn't a model. This rotating arrows is not a model having any correlation whatsoever to the actual facts. It's just incidental to the fact that we know the distance is causing the effect. The distance between the two surfaces is causing the change in the reflective index. That's it. That's the variable. He gives no insight into why distance changes the atoms. I have told you why it changes the atoms, because the atoms are all connected to each other and they can't change, you can't change the vessel size without changing where the atoms are located or how they're stretched or compressed.
What's going to be in the fourth lecture? Nobody can find one.
So again, he says nobody can, and implying that nobody will, and that, it's okay. Nobody can find one. Well, nobody tried very hard, in my opinion.
It's worse. We're not so dumb. We're pretty advanced compared to the Mayans.
So yeah, we're pretty advanced compared to the Mayans, but yeah, not in some ways. You still haven't stepped out of this love affair with Wu.
We've analyzed it very carefully. We almost proved it's impossible.
So we analyzed it very carefully and almost proved it's impossible. I mean, it's impossible to figure out why changing the distance changes the atoms. That's impossible? I don't think it is. I just think you never even thought about it. I think they never even thought about glass isn't some sort of flat surface with no atoms on the surface. I don't even think they ever drew it as atoms. They're just too distant from I don't know what the right word. They're just so lost in their imagination.
Over a wide class of ordinary possibilities. If it's going to be any kind of a model, it's going to be at least as weird as this one.
No, it's going to be so obvious and so simple. It's going to be, embarrassing. It's going to be just the fact that there's only two things in the universe, force and matter. And when you move matter, you use up some of the force's energy. And that's how simple it's going to be.
The reason is that the answers from this are so simple. That is what's more complicated than that.
Right. What he's really saying is there's only one stupid variable. How complicated can it be? It's just the distance is the only thing that's changing. So, yeah, it's got to be a pretty simple answer.
But mathematically, those forms and those curves are mathematically so simple, and the rules are so simple, it's hard to make any mechanism at all that can reproduce such simplicity.
Right, and it's really easy to do. You just turn the atoms. So the atoms have a little bit of a shape, they're a little longer than they are wide, and all they do is turn. Oh, can't turn anymore, atom gone, straight again. That's all.
The Mayan thing was really fairly complicated. The numbers were peculiar. There's no explanation of it. This analogy, our numbers are not peculiar. They have an explanation for it. It's a different situation. One more thing about gravity.
It's not any different than the Mayan thing. There's a pattern, a reoccurring pattern. Okay, and that's what the Mayans had. And the Mayans couldn't figure out that Venus and orbits and planets around suns. They just didn't figure out all that stuff to be able to figure out why there's a reoccurring pattern. We can figure out why there's a reoccurring pattern here. There's a physical mechanism. Atoms change when you change the thickness of the glass. The position of the atoms changes, and those position changes are symmetrical and consistent and based on some kind of geometry, and the geometry just reoccurs when you finally polish the surface enough to actually be one atom's worth removed. When you change by a full atom, you've now you're wrecked to zero again, and then when you're a full atom, you're zero again, and full atom, zero again. Because there can't be half atoms on the surface.
I would just remind you, we don't really have a good model because when it comes to why is it that there's a force inversely as the square of the distance? And what do you mean inversely as the square of the distance?
Right, so even something that simple, right? So this one always bugs me. Like there's some challenge to explaining why there's a square of the distance rule, why gravity does that, when light is doing exactly the same thing, okay? So you have a pressure coming out, okay, symmetrical from a point, or you have a pressure coming in symmetrical to a point, right? So my whole point is that these pieces of matter, an atom, okay, the little bits are just sitting here, right? And they're constantly being bombarded by a force, a pressure from the universe that is substantially even, except when local circumstances change. That is, when there's an electron close or a proton close, these environments change, or somebody shoots a laser beam or whatever. But it's exactly the same thing. Pressure coming from the outside, even in all three dimensions, is exactly the same as light leaving a light filament in all three dimensions. And that's the inverse square law. It's just the fact that the light is spreading, technically, metaphorically, however you want to describe it, and it's doing it in a square fashion. It's spreading this way, and it's spreading this way and this way with distance, and that's the R squared rule. So again, why would I have to say, why is the universe mathematical? Well, it's just the rule of anything existing as a point in a three-dimensional world and interacting. You automatically have an inverse square law if you have symmetry.
That's mathematical. And Newton taught us that we can make progress if you stop arguing about that. He said, I make no hypotheses, I don't explain the gravity.
Right. Well, that's not what you're saying. You're making a hypothesis. You're saying God plays dice with the universe, so this is almost silly. Newton didn't say God plays dice and makes gravity. God makes gravity. Newton was a religious kook and he didn't say that. He says, I don't fucking know. That's what he said, okay? And you guys aren't saying, I don't understand. You're saying, I'm going to put a placeholder for understanding. I'm going to bend space, nothing. I'm going to create all kinds of silly answers to the question instead of saying, oh, we haven't figured it out.
Law. I tell you what the law is, that tells you how the things look, and you can predict where the stars are going to be, and that's the pattern, but I don't, at the moment, know. But he left open the question, just like you asked. Maybe tomorrow somebody will figure it out. On your particular question, it's always possible that tomorrow somebody will figure it out, but it's going to be very difficult and very strange.
See, that's what he says. It's going to be this, this, and this because I didn't do it, and because I didn't do it, you can't do it. That's all he's doing with this smug little smile. He's just basically saying, I didn't think of it, and you're stupider than me, so you people are hopeless, and you'll never know because I didn't know. That's what he's saying pretty clearly. It's just a joke. He's not admitting that he doesn't know. He's basically saying it can't be known because he doesn't know it.
Do you like the idea that our picture of the world has to be based on a calculation which involves probability?
Not really, if I get right down to it. I don't say I like it, I don't say I don't like it. Right,
so this is just, of course you should have some opinion on whether you think it is there any point in being a physicist, in my opinion, if you're going to sit there and say at the fundamental level it's whack-a-verse all over the place. Just anything can happen. God can do whatever the fuck he wants. I mean, it's just a silly starting point for figuring out what happened. It's just introducing to a crime scene the possibility of the invisible man. Well, you're done then, right? There's no criminals anymore because everybody can use that out. The invisible man did it. Why? I mean, just imagine what would happen to the criminal justice system if they opened the door to invisible man as a viable explanation. And that's what physics did. It opened the door to something that just ruins any kind of rational grounded conversation.
Very highly trained over the years to be a scientist. And there's a certain way I have to look at things. When I give a talk, I simplify it a little bit. I cheat a little bit to make it sound like I don't like it. What I mean is it's peculiar. But I never think this is what I like, this is what I don't like. I think this is what it is and this is what it isn't. Okay? And whether I like it or I don't like it is really irrelevant. And the
real point is that whether it's an open question or a closed question, and the point is you close the question. You've closed the door to figuring out, well, why do the atoms change when the distance changed? You closed the door.
Believe it or not, I have extracted it out of my mind. I do not even ask myself whether I like it or I don't like it, which is a complete irrelevance. It's kind of a dumb answer, but it's true. And when I'm
Right, because he's not trying to figure out mechanically how the universe works. He's just trying to figure out what math works. And physics isn't math. It just isn't.
lecturing, I shouldn't have said I don't like it. What I was trying to say is you probably don't like it. There's nothing I think we can do about it. It might have been something else. I don't know how else to express it. It's not really personally a dislike.
Have you left out anything in this lecture which you need to add later?
It's a very difficult, and I worked very hard on the lecture to try to use as my examples things that I didn't have to change later, the interpretation slightly. You know, I couldn't get an elementary enough process that I didn't have. Later on, I have to make a little change. You see, we talk and we see as though it's reflected at the surface. Actually, what's really happening, and with a deeper understanding, which I should do later on in the lecture, I might forget, is that it's reflected, like cause, it affects electrons in here, which re-emit light here, or here, or here, or here, or here, or here. And what really is the things that we have to add is not the arrow from here and the arrow from here, but a whole lot of little ones from all the distances from there to there. But
Okay, so he says, right? Now, that's, to me, a mistake. And I think there are logical proofs to indicate that it is, in fact, the surfaces. That the light isn't reflecting from different locations, and it's sort of like the refraction of light sort of demonstrates it, because the light actually does bend going through the glass and would be reflecting from a lot of different positions, and that would make a mess out of everything. So I don't think that argument can be sustained. And the fact is that the surfaces are transition places, places where the angles change, like in a prism. And it's kind of clear that it all happens at the surface. All of the change happens at the surface, and then when it gets through the surface, when it's going through the surface, it's really being transmitted. It's like it's a sound when it's going through, and it's just movement at the surface. You know, it's a very specific kind of transmission between electrical, like. It's like electricity that's going through versus heat. That, you know, you can get both, but one is different than the other. And so I'm saying that I'm not prepared right at this moment to make the proof for it, but I'm just saying I think he's wrong. I don't think the light actually does reflect from all these layers. It does actually reflect at the surface, hits a proton and reflects, or it goes through. And if it's going through, then it's being transmitted by the pressure between electrons. I think reflections are hitting a proton, and I think transmissions are hitting electrons. Probably. Maybe. Possibly.
believe it or not, you get the same answer. Okay? So what I really ought to do, and I would do if I were doing it correctly, would be to talk about the reflections from every interior part and adding arrows. But I would rather add just 2 arrows the first time than an infinity of them. So I didn't cheat a little bit, but I got myself in a slight hole, which you picked up. The actual reflection is from the material. The electrons in the material.
So he's just saying I can cut the distance down to all of my, infinitely small pieces of distance, and I could just make an arrow for each one of those infinitely small pieces of distance, but they'll all cancel out. All of those little arrows will cancel out, so they're irrelevant. The only distance that really matters is the complete distance, because that'll tell you how many atoms you broke, or had half an atom. So he's just saying you're going round and round and round, or you could calculate it at every single point that the distance is changing. The clock's going around is just time. So you could do the calculation at every single hour as it goes around, but there'd be no point because every time it goes around in one cycle, it just canceled all the other arrows out.
In the case of Newton's thing, it's because the electrons which are reflected from the glass here and here are interrupted in their pattern. When you add the arrows, it comes out to be, believe it or not, the same as you just take a one from here and one from there. Perhaps just for those who can, I don't want to make it too hard, but just to give you a clue of the marvelous way it works. If you added tiny arrows to represent reflections from everywhere, instead of just talking about reflected from here to here, which is a good equivalent way. But if you took a whole lot of little baby arrows, each one a very, very tiny angle from the other, all the same length, which is the reflections from all these places, you see you generate a circle.
You go from point 1 to point 2 to point 3 to point 4 to point 5, and then you finally get to 2.9. Okay, and then you go to 3.
I shouldn't talk about the reflection from the front surface and the reflection from the back surface. I should talk about the reflection of all the stuff in between. And it's but it's equivalent. The net result of going around here is the same as going up here and back on that one. It even accounts for the minus sign. That is, the distance from here to here is what you get by putting onto this arrow this one backwards. Well, I got the distance is the same. See? I got it upside down. But this line is the same line as you would get by going in a circle. So it's really reflected from the interior. But in the first lecture, I thought I'd just get two arrows instead of an infinite number.
Does your picture apply to anything besides electrons and light?
This aspect is universal over the whole of the world's phenomena, as far as we can tell.
Okay, so this part is silly. Everything doesn't have a consistent reoccurring pattern. This only works with systems that have reoccurring patterns. Systems where you break it, make it change. You know, where the change flips. You know, where I don't know how to say. It only happens with things that have a consistent frequency, things that have a consistent cycle. So non-cyclical things, this won't help you at all.
Not just the light and electricity. This phenomenon of drawing arrows and making areas for probability. Probability amplitudes, we call them. The amplitudes and the probabilities are the squares of these amplitudes or the circles of them. That's universal. The next problem is a rule for how to draw arrows under different circumstances. What kind of arrows do you draw under different circumstances? What are the rules? One of the rules I told you is it turns at a certain rate for light and so on. Those are the rules that we do not know well in the case of the nuclear phenomena. But we know virtually exactly, or at least as far as we can tell experimentally. I lost my numbers. For electrons and light, the rule for how to make the arrows is apparently completely known. Nothing is ever complete. But within the accuracy and so on, it's known. What's not known is how the rules for making the arrows. Yeah,
well, again, they have no model that's coherent, sensible, that you could draw. It's nonsense. It's mush.
When it's photons that are moving around and so on. Okay.
When you are looking at something, do you see only light, or do you see the object?
The question of whether or not, when you see something, you see only the light or you see the thing you're looking at, is one of those dopey philosophical things that an ordinary person has no difficulty with.
It's really not that dopey, because this gets to relativity and the fact that information gets to us at slowly. It has to go through a force. It has to go at the speed of light. So it has to be an interaction. So yes, we always see things in the past. We never see anything as it is at this exact moment. At the moment we're seeing it, it's not the moment that that thing is experiencing.
But even the most profound philosopher, sitting eating his dinner, has many difficulties making out that what he looks at perhaps might be only the light from the steak, but it still implies the existence of the steak, which he's able to lift by the fork to his mouth. The philosophers were unable to make that analysis and that idea.
So this, this mocking of philosophy, whatever. These aren't even philosophical questions anyway. They are physics questions. These don't require you to do anything that complicated. Can you hear a tree fall? Does a tree make noise if it falls and there's nobody around to listen? I mean, yeah, it makes noise. It's the same damn thing. Nothing changed. There's still vibrations traveling. Yeah.
I've fallen by the wayside through hunger.
Starvation would have been a better word than hunger.
Can you tell us whether in the future your theory will be found to be wrong, or is it complete?
No, of course not. How can we know what the final thing is? I tell you only what we know today. Can I tell you more? Do you want me to tell you more? Would you like me to tell you what we know tomorrow? I'm sorry. I have the Nobel Prize from the past, not from the future. I do not know the future. And I answer in a similar way to your likes and dislikes. If you ask me what I think will happen in the future, I'll tell you I do not think. I do my best.
Right. So, that's probably one of the things that, limits you, is the fact that you probably should imagine it done better, in the future. What would the future do? That's kind of a high standard to apply to yourself, and then you'll say, well, yeah, the future wouldn't be stupid enough to be religious, and the future wouldn't be dumb enough to do this, and lots of things the future wouldn't do, so why am I doing them now? Why don't I try to be a future physicist and try to recognize that there should be better answers than bent space and whackatons.
To understand what supposed to understand what we know so far. I do not know what you're going to discover next, okay? I can't. I know only you're talking about the edge of the discovery business. And it's impossible to say what's beyond the edge. So I can't answer you.
Yeah, I know, but you have all kinds of evidence. And the fact is you put the evidence together in really sloppy and things like the Eddington experiment are glaringly underdone. I mean, it's not just a little bit underdone, it's glaringly underdone. You haven't repeated the damn thing. You haven't tried it with better technology. I mean, it's glaring. In this two-slit experiment, it's glaringly underdone as an experiment. Again, I can't cite some experiment where they actually did this thing where they calculated the total energy of a beam of light going into a system and then attempted to account for all the photons and account for all the ones that are missing. So none of this has been done to any kind of reasonable level. So there's just all kinds of evidence of this underdoneness is got to be symptomatic of probably mistakes.
All right. Except to say that the history of physics has been that the things that looked like they were nicely set aside turned out to be erroneous upon further discovery.
Well, exactly the opposite is sort of true. That there's some things that are discovered become rock solid, reliable things, and they'll never change. The inverse square law. It's perfectly understandable as what radial force does when it leaves a point source at different vectors. That's what it'll create, and so it's never going to change.
And since society continues to be vigorous enough in its endeavors to investigate nature, it's almost sure, from a social point of view, not from a theory of physics, that new things will be found out which will not fit in, and that we have no way to tell whether some young man, perhaps from New Zealand or somewhere, will find another way or more about this stuff, so we'll have a different picture in the future.
Right. So he's just talking about it as if we need some kind of new discovery, that we don't already have evidence and that we already have reason to doubt. And he's just pretending that, oh yeah, we're in a pretty solid boat here. And that's part of the problem.
I tell you what it looks like today. You call it my theory. It's not my theory. It's the theory everybody uses.
Yeah, it's a theory everybody uses. See? So, yeah. Well, I never used it. I never believed it. So anyway, I think we're done. All right. So just to point out again for the gravity argument, like I said, this key point that if you just understand that a tiny bit of energy is consumed, okay, by the process of force interacting with electrons and protons, that every time an electron and proton moves, it is in fact degrading a piece of the energy in the universe while the thing is moving. Now the piece goes back to its normal state once it stops moving the matter, but while it's moving the matter, it has some element of its momentum has been consumed, destroyed, and you can never put it back, okay? It happened in the past and it can't be undone. It got used up, and so something going the speed of light changes its momentum, moves slower when it's pushing a piece of matter. That degrade in the energy, okay, exists, and it's now moving in every single direction, okay? So every little object radiates just by jiggling, just by moving in space, radiates less force back to the universe than came in. So a certain amount of force came in, okay, 1 unit of force, and 0.9998 or something like that amount of force radiated back, and it was consumed by the motion. So in every direction there's a lack of force reflecting off of objects, every single one of them, and that's the origin of gravity. So gravity is just a consequence of the fact that when force interacts with matter, the force is degraded while it's pushing the matter. And so at every moment, as I pointed out, the matter can either be being pushed by something going this way, or it can have nothing pushing it, or it can have something pushing it this way, right? Or that way, this way, but these are the only state it can be in. Either something's pushing it or nothing's pushing it. Now, when it's in the nothing state, it's not going to create gravity because it's not reflecting anything at this moment. It's not consuming anything. But 50% of the time at least, it's in the moving state. And when it's in the moving state, okay, it's consuming energy. It's destroying it. It's converting a force that has a certain momentum into a force that has a little bit less momentum. And that explains the origin of gravity. Charge, completely different. Alright, so that's a good clarification, I think. It's such an elementally easy to understand reason why every little tiny thing in the universe, every piece of matter ends up creating gravity is because it inevitably moves. The universe is never perfect in how it's hitting it. There's always a little bit more energy coming from one side than the other side at any one moment, but in the end it'll be the same, 50-50 in terms of heads and tails. It's just heads and tails coming at you. In any 1 minute you have one extra head this way. So you're consuming energy in that direction. In the next moment, you'll be consuming it in the opposite direction. So in every one moment, you're consuming energy in some direction. And when you put a whole bunch of matter together, you're consuming energy in all directions. Oakley doke. I don't think we'll do comments because this has really been long enough. So anyway, so till the next time. But lots of good stuff in there, right? Yeah, I think it's good stuff.